All right, we are continuing our discussion of the Walras law. Okay, so, all right. Okay, so what do you see here again is, let me just explain once again. So we assume that each person, each household, H, spend entire income for consumption purposes. So this is the budget constraint again. So this is budget constraint of H. Okay. Then I take a big summation over households, right? For both sides, I sum the entire income spent in the economy here. Okay, so this is that. And then I find the summation of entire consumption expenditure in the economy. All right. Now, nice thing about this representation is that it is easier, of course, but you will realize that PI's prices are fixed for each household. Okay. This allows me to switch the summation signs and write it in this way. All right. The same equation. Now it is at the economy-wide level. Right. So what I see here is basically, oops. This is basically, oops, total demand for commodity I, and this is basically the total supply. Okay? Because this is demand for commodity I for each H. If I take the summation over H, I'm summing consumptions or demands by the household. So at the end, I find total demand for commodity I. Similarly, this is the supply of commodity I by household H. If I take summation over households, I find the total supply or total endowment of commodity I. All right? But then I can write this, right? PI, KI, PE must be equal to PI, EI. All right? Now, once again, realize prices are common. So I can write it in this way. PI, KI, PE. Oops. Okay. Minus EI equal 0. All right. Now this thing is now, okay. This thing is now the excess demand, right? Or more specifically, we can actually denote in this way. All right. Now this becomes the excess demand. So at the end, I have PI times excess demand summed all over the commodities equals 0. Okay. Now be careful. For this to happen, for this result to occur, right? What did I assume? I just assume that income equals expenditure, nothing else. And more specifically, I did not assume P is equilibrium, okay? P is any price vector, okay? So this result does not require P to be the equilibrium price, okay? As long as people spend all of their income, okay, then this result prevails. Now, what is the importance of this result? Well, it is called the Walras law, okay? In a pure exchange economy, the total market value of excess demand quantities is equal to 0. All right? Now, what's the importance of this? Well, let me write it in this way. Okay? These are the same two equations. So what do you see? If these markets are in equilibrium, which means, all right, so equilibrium means, of course, excess demand is 0, then the last market will also be equilibrium, will also be in equilibrium, right? So usually we say if n minus 1 markets are in equilibrium, then the nth market is also in equilibrium. All right? So this is the Walras law, and once again, it does not require this. Okay? Not required. Okay? So we are interested here, once again, in the total market value of excess demand levels. Okay? If all markets are in equilibrium, but just one, then that market must also be in equilibrium by the Walras law. Okay? Now, what is the implication of this? Well, usually we define the Walrasian equilibrium in this way, right? So it is a price vector. So let's write a formal definition. The Walrasian equilibrium in a pure exchange economy is a price vector P star such that Pi, or maybe I can write it in this way directly. Zeta I P star equals 0 for all I. Okay? So I will look at each market. Okay? In each market, I must see at these prices, these are the equilibrium prices, at these equilibrium prices, excess demands must have 0, must be 0. All right? So what's the implication of this? Well, how many unknowns do you have? You have P1, P2, ... Pn star. All right? So these are your unknowns. Right? These are your endogenous variables. So how many equations do you have? So the number here is n. So how many equations do you have? Well, let's count. You have zeta 1 P star equals 0. Zeta 2 P star equals 0, ... Zeta n P star equals 0. So you have also n equations. Then you must think, oh wait, I can solve this system, right? I have n unknowns, n equations. No, you cannot, because you don't actually have n equations. Why? Because of the Walras law. These equations imply the last one. Okay? Or these equations imply the first one. So one of the equations does not give you genuine information about the price system. Okay? It already tells you what you know by knowing these n-1 equations. Okay? In other words, this system is, if it is a linear model, let's say, it is linearly dependent. Okay? Because of this dependency, you need to provide new information to the system. Okay? To find prices. And that is entirely intuitive. Why? Because there is no such thing as, as absolute price. Prices are always relative to some common standard. Okay? If you, for instance, exchange, let's say 3 chairs with 1 table, then there is there is a price, 1/3 or 3/1. Okay? So any price is a relative price, and it doesn't have to be a pure exchange economy. Even in modern economies, there is a reference category here, right? So imagine the coin in your pocket, 1 Turkish lira. Okay? That 1 Turkish lira, if you imagine this as a commodity for a second, you will realize that you cannot sell this commodity by a price higher than 1 lira, right? Because its value is 1 lira, 1 Turkish lira. So you cannot exchange it for a larger price than that. Also, you would not, again, sell it for a price lower than 1 Turkish lira, because again, its value is there. So then Turkish lira, the money itself, becomes a reference category. All right? And we then express all the prices in the economy relative to that. Okay? You go to the market, you purchase oranges, and you pay, let's say you purchase 2 kilograms of oranges, right? So you pay, let's say, 10 Turkish liras. So what happened there? So what's the price? Price is 5 Turkish liras per kilogram, right? So it is 10/2, right? So that's the idea. Because you give them 10 Turkish liras, and in exchange, you received 2 kilograms of oranges. And right there is a price. The relative price is there. 10/2, which is equal to 5. All right? So that's the logic. And then you must include that in the price system, because again, these equations are not independent because of the Walras law. So if people spend all their incomes to consumption expenditure, then eventually Walras law is true. So if all the markets are equilibrium but just one, then the last one must also be in equilibrium. So that equation does not, give you a new information, a genuine information about prices. So you need to provide that genuine information. Now, there are several ways of doing that. One typical assumption is this. So you choose a particular commodity and you assume that its price is equal to 1. As in our example of oranges and Turkish liras. Okay? So this is a price normalization. Or you can define price indexes. Okay? One simple index we are going to use is this. This is basically it's actually called unit simplex. Okay, but right here, be careful. You are introducing new equations. Okay. Right here, I introduced an equation. Right here, I introduced an equation. Remember, I just only need one equation. One equation to make the system solvable. Okay? You can also define something like this. Doesn't really matter. As long as you give me one equation about any of the prices, I can do it. You can also do this. Or this, or any other number you may want to choose. Okay? As long as there is an equation, then I am good. All right? So, in some models, we're going to use this. In some other models, we're going to use that. In some more complicated models, you can define more realistic price indexes. Okay? Of course, that depends on your preferences as well, right? The consumption basket. Okay? Here, for instance, you can define this as a price index, and then you can talk about inflation where, price index is growing, such as 3%. All right? So then you can talk about more specifically about inflation rate, for instance. Okay? All right, so let me just stop for a moment here. And if you have questions or comments about all this, we can discuss them right now. Otherwise, I will switch back to our discussion on existence. So I will move to the next topic on my agenda. So let me very quickly summarize what we did here. We define an exchange economy, a pure exchange or endowment economy. So we give people, many people here are there. We give people some commodities, and then they have some demand functions over these commodities, and they exchange. Okay, they exchange these commodities with each other. Eventually, there is market clearing. Okay, so we define equilibrium in a particular way. We say excess demand must be zero in each and every market. So total demand must be equal to total supply. So that's the definition of general equilibrium, because we are counting each market separately, and in each market we require equilibrium. But then I also discussed, for any price vector, as long as people spend their entire income to consumption expenditure, there is something called Varroa's law. So if all markets but one clear, that last market must also automatically clear. Because of this law, we have to provide new information to the market model to solve for prices. Okay? So under the price normalization, by choosing one of the commodities as the reference category and equate its price to 1, then we can express all the prices relative to this one. Okay? So that's the main story that we just did for today. But if you have questions and comments, I can answer them. Otherwise, I will move to the next topic. Are you there? Okay, this is, let me just remind you of one thing as well, while you think about your questions. So notation is a bit cumbersome. It's a bit tedious, but it is not that difficult. So this is very simple. So everything you already know. This is in that regard straightforward, but you think about what you are writing on the board, or what we are writing on the notebook. Okay, so it is not so at first it is a bit intimidating, but not that difficult. So it's gonna be slightly more difficult in the upcoming weeks, but not that difficult for now. Okay, any questions? All right then. Let me now move to the existence part. Okay. It still records. All right. Now let me talk about the existence of the Walrasian equilibrium. Now, let me remind you, we have 3 topics here. One is existence. The other is uniqueness. And the third is stability. So we're gonna discuss each other in turn, right? Now, to talk about existence, we want to do this normalization, okay? P1 plus P2 plus dot 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 Pn equals 1. All right? Unit simplex. So this is the normalization we are just going to use. All right? So all the prices must be equal to 1. And how can I do that? Well, it is again, since prices are relative, I can play with them. All right? Doesn't really change anything because I know, because of the Walras law, eventually I need to impose something about these normals, something about these prices. And here I normalize this. I introduce this normalization. Okay. So this, of course, creates a set, right? So that set is, I mean, it can be defined in this way. So it is so a typical element is a price vector in this set. And to be in this set, these prices must satisfy that. Okay, again, this is called unit simplex. You may imagine in 3 dimensions, if you have P1, P2, P3, you have something like this. Okay, a rectangular plane, sorry, a triangular plane residing in this. Of course, these are just one. Okay, in 2 dimensions, it is of course like this: P1, P2. You have that. Or actually, sorry. You have that. Okay, this is 1. This is 1. Okay, because here on the blue plane, any place on the blue plane, this is a plane, not the pyramid. Okay, so prices sum to 1. Okay, again here prices sum to 1. P1, P2, as in here, right? P1 plus P2 equals 1. Here you have P1, P2, P3 equal 1. Okay, I have 10 minutes. All right, so that's it. So now I will also define the Gale-Nikaido mapping. Okay, now here is the idea. For existence, I need to model the price adjustment mechanism. Okay, now you know this graphically, right? So this is, let's say, quantity. This is price in any market. So this is supply, this is demand. Let's say price is here. Okay, at these prices, at this price, let's say P hat, what do I have? Supply is greater than demand, right? This is supply, this is demand. So excess demand is negative. When excess demand is negative, price must decrease, right? So when price decreases, I'm here. Again, excess demand negative. It must decrease again. Eventually, I reach the equilibrium. All right? Now, I need to model this for n prices such that price vectors are element in the unit simplex. Okay? That's the key. So how do we do that? To do that, we define the Gale-Nikaido mapping. Okay, again, it's a price adjustment mechanism. So we define a function phi from S to S. Okay, what does it mean? So P will be an element in S. Okay, that will be the argument of this function, and phi of P, these are the adjusted prices, they will also be in the unit simplex. Okay, so this is the price adjustment mechanism, the Gale-Nikaido mapping. All right, and the formula is this: for the ith commodity, I have Pi plus the maximum of zeta I P 0. Okay. On the denominator, I have the other prices. Okay. Now that's the Gale-Nikaido mapping. All right. So what's going on? Well, there are three properties that this function should satisfy. Okay. Three properties to be satisfied. Okay. Now I will explain each one. Let me use this area. First, if we are at equilibrium, we must have no adjustment, right? Right? Does everybody understand that? Because if I am already in equilibrium, if P is already equal to P star, then there must be no adjustment. So this mapping should realize that we are in equilibrium. We are in equilibrium. This is the Walrasian general equilibrium. Every market clears. So there must be no updating in the price, right? So phi of P star must be P star. Second, updated prices must be in S, right? So updated prices should sum to 1. These are updated prices. Oops. Okay. What's the problem? Okay, for some reason, it's not switching. Okay. Okay, I have a problem here. All right, okay. So the second property is that updated prices must also be in this set. Okay, so their summation must be equal to 1. All right, that's the third property. So the second property. The third property is that if excess demand is positive for some market, okay, then updated price must be larger than the supplied price, okay? Right? Because excess demand is positive, the price should increase. Okay? So three properties that the Gale-Nikado mapping should satisfy. All right? Now I will show you it actually satisfies all three. The first one is very simple. So the first property, remember, in equilibrium, there must be no adjustment. Okay? So remember the Gale-Nikado mapping. Phi star, in that case, of course, Pi star plus maximum of zeta I P star 0 divided by 1 plus summation from j equal to 1 to n max zeta j P star 0. Now realize that all of these are equal to 0, right? By definition. This is the Varrozi in equilibrium. In equilibrium, all the markets clear. So the ith market was also clear. The same is true for this. All of them are equal to 0. So the maximum of 0, 0 is 0. All right. So this entire term is also 0. So what you have is, you have Pi star plus 0 divided by 1 plus 0, you have Pi star. Okay, once again, we have less than 1 minute. Let's meet at 10:55, okay? About 15 minutes because the conversion takes too long. All right, 10:55. All right, everybody. Okay, 10:55, I will see.